Thank you, Professor Panda. This work has been done with my PhD student, Jungyeon Jo. He's sitting there. He plans to graduate in coming winter. So he's looking for a research position now. So if you are looking for a candidate who knows both MPI and operating system, I would like to say he's the man. Okay. So today I'd like to, I will start with a brief introduction to MPI intranode communication, and I will share our preliminary experiences to optimize intranode collective communication based on MBAP2. And I will conclude my presentation. So as the number of cores integrated in a process package keeps increasing, the intranode communication becomes more and more important. Sorry for showing only Intel processors in this slide. But anyway, therefore, many researchers try to optimize intranode communication, and we can classify those efforts into three categories. The first one is loopback. In this approach, the network interface card figures out whether the destination process is running on a remote node or running on the same node. And then if the message is heading to the local process, the network interface card simply DMAs the message into the destination buffer. So there are two DMAs in this approach. Another approach is to use shared memory shared between processes running on the same node. In this approach, the sender copies the message to the shared memory, and the receiver copies the message from shared memory to the destination buffer. So there are two data copy operations in this approach. And since data copy has the lesser overhead than DMA operation, so the shared memory shows much better performance than loopback. However, there are two copy operations. So to reduce the number of copy operations, researchers proposed a memory mapping mechanism. In this mechanism, the source buffer is mapped to the receiver's address space. Then the receiver can directly copy the message from source to the destination buffer by means of kernel level support. As Professor Panda just mentioned, LIMIC was the first implementation for this kernel level support, and it is being released with MBAP2, and you can enable it by using these commands. And there is another implementation of kernel level support for memory mapping called CMA. CMA is quite similar with LIMIC2, but CMA is implemented within the kernel itself, while the LIMIC is implemented as a kernel module. Currently, MBAP2 uses CMA as a default kernel level support for memory mapping. And also there is another implementation called XPMEM. XPMEM is different from LIMIC2 and CMA in that XPMEM maps buffers into the user level address space, while LIMIC2 and CMA map the buffers into the kernel level address space. The kernel level support performs memory mapping, which have some level of overhead. Therefore, this mechanism is only beneficial for the large messages. So MBAP2 uses shared memory for small messages and kernel level support for large messages in point-to-point communication. However, in collective communication, things are much complicated. So today I'd like to discuss more about intranode collective communication, and particularly I will focus on the MPI Bcast and MPI gather in this presentation. As you know, MPI Bcast and MPI gather have one-to-many and many-to-one communication semantics respectively. MBAP2 uses the collective aware shared memory to implement MPI Bcast. On the other hand, MBAP2 uses a point-to-point communication channel to implement MPI gather, which means that it internally uses kernel level support for large messages. So let me first closely look at MPI Bcast. This slide shows the current implementation of MPI Bcast in MBAP2. The root process copies the message into collective aware shared memory, and the other processes copy the message from shared memory to its destination buffer. It is to be noted that these copy operations in the step 1 and step 2 are performed in 8 kilobyte data blocks unit, which means that data copy operations in step 1 and 2 can be overlapped for different data blocks. But then we wondered why MBIPG2 didn't use kernel level support either CMA or LIMIC2. So we experimentally applied LIMIC2 instead of shared memory for MPI Bcast. And this graph shows the performance measurement result. Since this graph shows the latency, lower numbers are better. So LIMIC2, the orange line, shows worse performance, significantly worse performance than collective aware shared memory. Before these experiments, we expected that MPI Bcast with LIMIC2 would work like this. The root process sends the descriptor of source buffer to the other processes, and other processes would perform memory mapping, data copy, and memory unmapping. And we expected that these operations on non-root processes would perfectly overlap as shown in this figure. However, it turned out that the memory mapping operations cannot be overlapped because of the spin lock in the kernel. So as shown in this figure, the operations in non-root processes were performed in sequential manner. So we modified the LIMIC2. We call it LIMIC2 overlap in this presentation, so that we can move memory mapping operation to the root process, and the other processes only perform the data copy operations. So now we can expect that the data copy operations on the non-root processes can be overlapped perfectly as shown in this figure. And we measured the performance on a 20-core system and a 120-core system. And this graph shows that LIMIC2 overlap could reduce the latency of MPI Bcast up to 84%. So this is very good. But then we had a question of why MBIPG2, more precisely collective aware shared memory, doesn't show a comparable performance to LIMIC2 only. So I just want to remind you that the copy operations in step 1 and 2 can overlap for different blocks. Then the shared memory should achieve a comparable performance to one copy approach. To analyze the high latency of this shared memory, we measured the overhead of data movement from source buffer to the destination buffer for each process. So blue bars in these graphs show that the data movement overhead, and though there are profiling overheads, especially in shared memory case, there are huge gaps between LIMIC2 overlap and shared memory. To analyze further, we break down this data movement overhead as shown in the next slide. So the orange bars in the right side figure graph represent the data copy overhead for each data blocks. So each bar contains the copy overhead in the step 1 in this figure, step 1 copy overhead, and the copy overhead in the step 2. So if the copy overheads are perfectly overlapped, it should show like left bottom figure. Here we can state for different blocks, the copy overhead for the step 2 and step 1 can be overlapped. So if we return back to this actual measurement result, I mean the right side graph, at very first time, the overheads are perfectly overlapped as we expected, but later on, somehow the copy overhead becomes large, and sometimes the overheads are not overlapped at all. So we need further investigation to figure out what are the exact reasons. But currently, one thing we found is that this shared memory performs kind of flushing operation to maintain the shared memory in a reasonable size. So there is no point. Okay. Yeah. Okay, thank you. We can see that here and here we can see that there is no overlapping at all. And these are the points where the flushing operation happened. So these are the reasons why we couldn't observe a comparable performance with comparable performance to LIMIC2 only overlap. Okay, now let me move on to the MPI gather. And this slide shows the current implementation of MPI gather in MBABICH 2. First, the root process allocate an intermediate buffer. Then the other processes send their message to the intermediate buffer. And once the messages are gathered, it is copied to the final destination buffer. So since these non-root process send the messages to the intermediate buffer through point-to-point communication, if these messages are large, it will go through the kernel level support by using the memory mapping. So to see whether it is okay to use kernel level support for this step 2 data movement, we measure the data movement overhead by using LIMIC. And this is the result. Each blue bar represents the data movement overhead in step 2 for a specific process. And we reordered these ranks so that these bars can be sorted in an ascending order like this. And then we marked only data copy overhead. And then this is the result. And as you can see, these data copy blocks represent actual data movement. And this graph reveals that actual data movement is not overlapped. They are performed in a sequential manner. So let me explain the reason by using this figure. So CMA and LIMIC2 assume that only the receiver process performs the memory mapping and data copy operation. So in the MPI gather, the root process is the receiver. So it performs memory mapping and data copy operations for non-root processes in a sequential manner. That's why we cannot expect it overlapping of data copy operations. So in LIMIC2 overlap, we moved the data copy operation from root process to the other processes, so that the copy operation can be overlapped as shown in this figure. So again, we measure the performance on a 20-core system and a 120-core system. And here we can see that our LIMIC2 overlap could improve the MPI gather performance up to 88%. However, here we could see that LIMIC2 overlap shows worse performance, and we figures out that MBABICH 2 switched to a binomial tree algorithm in this case. However, our preliminary implementation uses a simple collective algorithm. So we are thinking that we have to consider a better algorithm for a large message and large number of cores. Okay, in conclude, we try to optimize the performance of MPI bcast and MPI gather by suggesting a new extended implementation of LIMIC2, which provides new interfaces that can support memory mapping reuse and flexibility of where the copy operation take place. And we showed that it could improve the performance of MPI bcast and MPI gather up to 84% and 88% respectively. as an ongoing work, we are trying to apply our LIMIC2 overlap to MPI scatter and MPI gather as well. And also we are seeing the significant performance improvement with these collectives. And also we are trying to overlap between collective communication and computation. In current implementation, collective communications are returned after some synchronization. But what we are thinking is to asynchronously return so that the computation can be overlapped with background communication. So this can be considered as similar with the MPI-3 asynchronous communication, but what we are trying to here is that we want to preserve the MPI-1 synchronous collectives while we provide asynchronous collective communication internally. And future work, we want to move forward LIMIC3 in cooperation with NowLab at OSU. And okay, this is what I prepared. And I have one quick announcement about workshop I'm organizing. And Professor Panda is also on advisory committee of this workshop. And we are gonna, this workshop will take place in the next week. So you might not be able to attend this workshop, but please be aware of this workshop and consider to submit a paper or participate in from next year. Thank you.